Hey everyone, and welcome back to the channel.
Sure. What if I told you that time near a black hole doesn't just slow down, it essentially stops? Not from the perspective of someone falling in, but from the perspective of someone watching from far away. An astronaut falling toward a black hole would cross the event horizon in what feels like seconds to them. But to us, watching from Earth, they would appear to freeze in time forever, never quite reaching the surface. This isn't science fiction, this is general relativity, and it gets even stranger. Near a black hole, the fabric of space-time becomes so severely warped that our entire understanding of time breaks down. Today, we're going to explore exactly what happens to time near these cosmic monsters, why Einstein's equations predicted this bizarre behavior, and what it means for the future of space exploration. Let's dive in. To understand what happens to time near a black hole, we first need to understand the relationship between gravity and time itself. In 1915, Albert Einstein published his field equations, showing that mass does not simply attract other mass through some invisible force. Instead, massive objects curve the fabric of space-time, and this curvature tells matter how to move. This is gravity, but here's the groundbreaking part. This curvature also affects time itself. The stronger the gravitational field, the slower time passes relative to a distant observer. This is called gravitational time dilation, and it has been experimentally confirmed here on Earth. Clocks at higher altitudes, where Earth's gravity is slightly weaker, run faster than clocks at sea level. The difference is tiny, just nanoseconds per year, but it is real. GPS satellites have to account for this effect, adjusting their clocks to match ground-based receivers. Without this correction, GPS positioning would be off by kilometers every day. Now, scale this up to a black hole, and the effect becomes extreme. A black hole forms when a massive star collapses under its own gravity, compressing all of its mass into an infinitely dense point called a singularity. Surrounding this singularity is the event horizon, the boundary beyond which nothing, not even light, can escape. At the event horizon, the curvature of space-time becomes so extreme that time effectively comes to a complete standstill relative to the outside universe. Imagine our astronaut again, free falling toward a black hole. From our perspective, billions of kilometers away, as they approach the event horizon, they would appear to slow down. Their image would become dimmer and redder, a result of gravitational struggles to climb out of the deep gravitational well. They would never actually appear to cross the event horizon. They would fade from view, frozen in time, their image slowly dimming to black. But from the astronaut's perspective, they would cross the event horizon in a perfectly finite amount of time, experiencing no dramatic change at the moment of crossing. This is one of the most bizarre predictions of general relativity, and it raises a profound question: if time stops.
If time stops at the event horizon from an outside perspective, does the astronaut ever really cross it? The answer depends on your frame of reference, and this is where things get deeply confusing.
Forget.
The first time I heard about this paradox, I could not sleep for days. How can two people disagree so fundamentally about whether something has crossed a boundary? The resolution lies in understanding that time is not absolute. It is woven together with space into a single fabric called space-time, and different observers can slice this fabric differently. What seems simultaneous to you may not seem simultaneous to someone else moving at a different speed or in a different gravitational field. This brings us to one of the most famous thought experiments in physics, the black hole information paradox. In 1965, mathematician Roger Penrose proved that under general relativity, any object that collapses to form a black hole must contain a singularity, a point where density becomes infinite and physics breaks down. Penrose proposed the cosmic censorship hypothesis, suggesting that all singularities are hidden behind event horizons, preventing us from seeing the breakdown of physics. But this creates a massive problem. Here's where it gets even more interesting. In 1974, Stephen Hawking discovered that black holes are not entirely black. Quantum effects near the event horizon allow black holes to emit radiation, now called Hawking radiation, causing them to slowly lose mass and eventually evaporate. A black hole with the mass of our Sun would take approximately 1067 years to evaporate completely. But here's the paradox. When the black hole evaporates, what happens to all the information about everything that fell into it? According to quantum mechanics, information cannot be destroyed, yet the standard model of Hawking radiation suggests it is lost forever. This is the black hole information paradox, and it has kept physicists arguing for nearly 50 years. Some propose that the information is encoded in subtle correlations in the Hawking radiation itself, Others suggest a firewall of high-energy particles at the event horizon. Still others, like string theorists, believe the answer lies in holography, that the information is stored on the two-dimensional boundary of the black hole like a hologram. So what would actually happen to you if you fell into a black hole? First, you would experience spaghettification, where the difference in gravitational pull between your head and feet becomes so extreme that you are stretched into a thin strand of matter. But let's imagine you survive somehow and cross the event horizon. From your perspective, you would cross in a finite amount of time, perhaps hours or days depending on the black hole's mass. But from the perspective of the outside universe, you would be frozen there forever, slowly fading away. And here is the strangest part. As you fall in, you would actually see the entire future history of the universe play out before your eyes, compressed into the moments before you hit the singularity. The light from distant stars and galaxies would blue shift and flood your vision, painting a cosmic movie of everything that ever happens after you cross that threshold. Recent discoveries have only deepened the mystery. In 2019, the Event Horizon Telescope gave us the first direct image of a black hole, the one at the center of galaxy M87, and it matched Einstein's predictions perfectly. In 2022, they imaged Sagittarius A, the black hole at the center of our own galaxy. These observations confirm that black holes behave exactly as general relativity describes, including the extreme warping of space-time around them. So what does all of this mean for our understanding of time? It means that time is far more flexible and relative than our everyday experiences suggest. It is not a universal clock ticking uniformly for everyone. It flows at different rates depending on your speed and your position in a gravitational field. Near a black hole, these differences become so extreme that our intuitive notions of before and after break down completely. What happens to time near a black hole? Time slows to a crawl, almost stopping at the event horizon. But this is not a simple answer because time also depends on who is asking. The universe does not give us a single clock. It gives us a web of proper times, each valid for each observer. And black holes sit at the intersection of these webs, revealing that time itself is far stranger than we ever imagined. Thanks for watching. Please subscribe to my YouTube channel for more interesting videos.